class. In this video, we're going to be doing a revision over bivariate data as well as univariate data. The reason why we're going to be doing a revision lesson today is because over the holidays, I'm sure most of you guys weren't probably doing any forms of revision at all, and I think it's a good way to start off the first day of the term. Before I go over and revise these two topics over here, I do want to talk about how will this subject change in response to the COVID-19 pandemic. Now, this subject over here, this further maths elective, was different compared to your maths A subject because in this subject, we predominantly rely on the CAS calculator in order to get our answers. However, because due to remote learning now, I can't actually supply you this CAS calculators, which I generally did in school, so therefore you wouldn't be able to obtain the answers which you would normally do. As a result of this, what this means is the implications means that I need to teach you the by hand calculations, which I already do, but I teach you both ways, by hand as well as using the CAS calculator. Now, since we don't have the calculator, it's just going to be solving all the questions by hand, and this is going to be the same case for your assessment tasks as well as your exams. As a result, what you'll find by the end of this term and in the lead up to the exam, this subject as well as Maths A is going to be pretty much identical in terms of the topics we cover, since there is a algebra approach focus for both of these subjects. Now, I'm aware that two or three students in a class already own a CAS calculator, and as a result of that, these particular students have a certain advantage compared to the rest of the class. So the assessment tasks that you guys will be doing over online over the next few weeks or so is going to be related to statistics, and obviously students who own these devices will have a slight advantage and can get more accurate results, more accurate answers than the other students due to this fact. And I can't really monitor this and prevent this from happening since this is all done online. But anyhow, let's just quickly move on to the actual revision components of the lesson. So firstly, we're going to be looking at univariate data. The purpose is to describe the distribution in terms of shape, spread, and center. There are three main types of univariate visual displays. These includes the box plot on the left hand side over here. In the middle, I've got something referred to as the normal distribution, aka the bell-shaped curve, which is something that you might refer to it as. And on the right hand side, I've got a histogram over here. But in today's lesson, I'm not going to be focusing on the histogram because this is something that's not really focused at all at the senior level. So I'll only be focusing mainly on the box plot and the normal distribution. So firstly, looking at box plots, what I'm going to be revisiting is how we calculate the 5-figure summary and how this actually allows us to draw the box plot. I will then look at how do we actually calculate outliers again by finding the lower fence and upper fence. We're then going to be describing the box plots in terms of its shape, center, and spread. So hopefully these words ring a bell. And lastly, we're going to be comparing these parallel box plots, so two box plots side by side, and comment on the differences between the two. Now, this is an example that we've previously unpacked in our previous lesson, but I'm going to be going over it again just so you have a better understanding, just in case you probably forgot. So the first question wants us to construct a box plot by hand. Now, before we can actually draw the box plot, what we need to do first is find the 5-figure summary. So what you need to do is notice that this data set over here is already in order. Once it's in order, you need to find the median. So remember, use the n plus 1 over 2 formula, where n represents how many numbers are there in the data set. In this example over here, there are 16 numbers. So therefore, if you go 16 plus 1, which is 17, 17 divided by 2 is equal to 8.5. So this tells you that the median value lies in between positions 8 and 5. So therefore, it's going to be between it's going to be between 1, 2, 3, 4, 5, 6, 7, 8. So in between these two numbers over here, as a result of that, the median is going to be the exact same thing, and therefore you can find out what the Q1 and Q3 is by finding the medians of those respective halves. So if you do this successfully, what you should obtain, what you should obtain is this over here. So minimum is 11, Q1 is 17.5, your median, which is also represented by Q2, is 25, Q3 is 32, and the maximum is 39. Once you do this, pretty much drawing the box plot will be relatively straightforward, and this is what you get. Now notice in this particular example over here, we don't actually have a context, so it doesn't actually talk about scores or marks or reaction times. If it did, then we do need to include a label or a title for our box plot, but in this case over here, since we don't have one, we don't need to worry about it at all. For part B, the question tells you to comment on the presence of outliers by finding the lower and upper fence. So the way we do this is, as such, we need to find out what the IQ are first before we can actually find out the lower fence and upper fence. Since the formulas for the lower fence and upper fence requires you to find out the IQR first. So remember, the lower fence formula was Q1 subtract bracket 1.5 times the IQR, whereas upper fence is calculated by going Q3 plus 1.5 times the IQR. So I've already got all the solutions I'm working out on this slide already, and as you can see, there are no values that are below the lower fence. There are no values that's greater than this over here is a typo. This is the upper fence up here. As a result, there are no outliers in this data set at all. Remember, we said that these lower fence and upper fence are these boundaries, and anything outside these boundaries are therefore considered to be outliers. We then looked at describing the distribution of a box plot, and I've given you this particular template that you could use to actually describe the distribution in terms of its shape, spread, and center. I do want to clarify that when there is outliers, then you do need to include this statement over here, but otherwise if there are no outliers, you don't need to include this statement at all. And the word variable over here, that kind of just, this is only included or necessary if the particular question had context. So if it was talking about reaction times, then your variable in this case would be reaction times. We looked at the shape of a box plot, and I do want to kind of go only over what this is because when you're trying to find out the shapes, it's quite subjective, and the judgment between me and you will be slightly different. So, for instance, one of the definitions of a positively skewed distribution is when the length of the upper tail is greater than the length of the lower tail. So what that means is, for instance, if this tail over here was a lot longer than this, that means this is positively skewed. So that's one of the definitions. Another definition of a positively skewed, and something that I generally go by, is that the distance between Q3 and Q2 is greater than the distance between Q2 and Q1. So as a result, since this is a lot more bigger, this is therefore considered to be positively skewed. So these are two types of definitions that that belong under positively skewed. Similarly, for symmetrical, we say that it is symmetrical when the whiskers, so these tails over here, are identical in length, but obviously this another way of defining a symmetric distribution is when this over here is in the middle of the rectangle over here, so pretty much at the center of the IQR range in this case. And for negatively skewed, these are the two other definitions over here, but I'm not going to read it through. You can read it yourself. We're going to go through this example over here of how we could actually use a template to comment on the distribution of a box plot. So in this example over here, when you're commenting on the shape, we don't really look at the outliers, Rob, because remember, outliers don't necessarily belong to the actual data. They shouldn't appear at all. So in this case over here, we're only going to be focusing on this over here. Now, in this case here, this is pretty much roughly symmetrical. So I want to say this has a symmetrical shape with a center or median value of, in this case, that's going to be 41. The variation between minimum and maximum, so it's asking you what the range is in this case over here. So if we're trying to find the range, it's going to be the smallest number. So in this case, the smallest number is 10. The highest number in this case is going to be 47. 47 take away 10 is therefore going to equal to 37. Whereas the IQR, so the Q3 take away Q, so this number over here, take away this, that would equal to 10. Now in this case over here, you've got 10, 15, 20, and 25 as outliers. And notice that I've cautiously tried to avoid saying there are 4 outliers. Remember, a box plot doesn't tell you the frequency at all. In this case over here, there could be many outliers in this case that have the value of 25, but a box plot doesn't tell you how many outliers there are. It just shows you any value that corresponds to this score, this mark over here, or this value is an outlier. So in this case, I said 10, 15, 20, and 25 are considered to be outliers, as it lies, in this case, below the lower fence, or the minimum fence in this case, and find out what the value is going to be, which is going to be 24 if you did the calculations. We're now going to be looking at commenting parallel box plots, and the trick that I told you to do was that you need to actually compare the SOCS, which is abbreviation or an acronym, which stands for the shape, the outliers, the center, as well as the spread. So we're going to look at this example over here of how we could actually use this abbreviation to formulate our answers. So we're going to first compare the shapes of these two distributions. So for 1973, this has a greater tail, so therefore this is going to be negatively skewed, whereas for the 1953, this is going to be symmetrically skewed. Symmetrically, you can't be symmetrically skewed, so it's going to be symmetrical. Now in terms of the outliers over here, both of these do not have outliers at all, and in terms of the center, all you need to do is just give me an approximate value of the median. So in this case over here, I'm approximating this is going to be equal to 52. I'm approximating the median value for this is equal to 62. Now, and there's no wrong answer at all, because we are approximating. You're kind of forced to approximate. For the spread is pretty much where you have to calculate the range as well as the IQR. So if you do the range and IQR, these are the answers you should get. Once you've actually figured out the shape, outlier, the centers, and the spread for both of these distributions, you need to make a statement where you compare each of these different aspects. So let's talk about the shape first. The way that I started off is by saying the distribution of the life expectancy. So notice that I've actually incorporated some of the context in this case. So this is something that you need to do for your answer as well. So the distribution of the life expectancy shows a symmetrical shape for one of the box plots and a negative shape for the other. So that's how you actually compare and contrast the two box plots. I'll then talk about what the center value is going to be. So in this case over here, I said that the average lifespan for this one over here is greater, and I've given the value over here just to kind of justify and support my response. And I've done that the same thing over here as well, 52 for this one over here. Once I've done that, then I'm going to be talking about the spread. So in this case over here, I said both distributions have no outliers, but the life expectancy is more consistent, meaning it's less spread. In 1973, because it's more compact compared to 1953, since it has a smaller range and IQR value. All right, now that after we've actually gone through some examples and gone over the theory a bit, what I like you to do now is I like you to answer some of these questions. So whenever you see a slide that has a timer next to it, this indicates that I like you to answer these questions. These are the questions that you haven't actually solved previously at all. So I like you to answer these questions, and this is the suggested time frame that I'd like you to complete it by. So please pause the video right now so you can actually answer the questions, and then after 10 minutes or after you've actually finished answering the question, then please continue playing the video to see whether your answers matches the answers that I actually have on the screen. So the first question reads, find the outliers for the following data set. Now, as you can see over here, this particular data set over here is not written in order, so not from smallest to largest. Our first step is to assemble the numbers from smallest to largest so that we can find the 5-figure summary, so that we can find out the IQR, so that we can find out the lower fence and upper fence that gives you the outliers. So that was a bit of a mouthful. So but first, let's first reorder the numbers from smallest to largest. Once I've done that, then I can actually find out my 5-figure summary. So in this case over here, I've kind of zoomed in a bit. So we're going to find out our 5-figure summary. We know that the minimum value is equal to 12. Our maximum value in this case is equal to 38. So these two values are always readily found when you're trying to find out the 5-figure summary. Once the numbers are in order, now you can actually find out the median. Now, I know that you can find the median by doing the n+1/2 formula that I've previously taught you, but notice that this particular data set is really small. So in this case, the more efficient method is by crossing out all the numbers from the outside and then progressively cancel out all the numbers in the inside and make your way to the middle or towards the center, because that's the definition of the median. So in this case, if I do that, I'll cross out these two numbers, cross out this, and I'll keep on going until I arrive to my center value. So after I've crossed out these two values over here, this implies that my median lies in between these two values. Well, in this case, a number in between 19 and 19 is also going to be equal to 19. So my median is equal to 19. Now remember, the median essentially separates the data set into two equal halves. Now, once the data set is split into two equal halves, you can now calculate what Q1 and Q3 is. Q1 and Q3 is essentially found by finding the medians of each of these respective halves. So you've got a lower half and you've got an upper half. To find out the lower quartile, you find out the median in the median of the lower half. So in this case over here, this would be 14. So Q1 is equal to 14 and Q3 is therefore going to equal to 27 in this case over here. Once you've found out the 5-figure summary, then you need to find out what the IQR is. So IQR, remember the formula is Q3 subtract Q1. We said that Q3 was equal to 27. 27 take away 14, that equals to 13. Now, after we've calculated the IQR, we can now calculate what our lower fence and upper fence is. If you recall, we'll calculate lower fence. Lower fence formula was equal to Q1 subtract bracket 1.5 times the IQR. So let's substitute all the values that we know into our formula. So therefore, lower fence is equal to Q1, which is equal to 14. 14 take away 1.5 times 13. If you put this into the calculator, you should get an answer of negative 5.5. And then after you've calculated the lower fence, please refer back to the data set to see whether there are any numbers below this particular number. In this case, there's none, so therefore that means there's no outliers below the lower fence. Now we calculate what the upper fence is. Upper fence, the formula for that is Q3 plus bracket 1.5 times the IQR. Q3 in this case was 27, so 27 plus 1.5 times 13. If you do this, put this into a calculator, you should get an answer of 46.5. Again, refer back to the data set to see whether there are any numbers that are greater than 46.5. In this case, there are none, so write a statement, no outliers present in this data set. Alright, now once we've actually determined the 5-figure summary, which we've done in part question 1, we could actually use this to construct a box plot in question 2. So if you did this, this is what your box plots should look like. It should look something similar to this over here. And if I was to comment on the distribution, all I do is identify what its center is, which is what I've done over here. So that's 19. In this case over here, this is positively skewed because this tail over here, the upper tail is longer than the lower tail. And then I need to indicate what the range is in this, which is the maximum subtract the minimum and the IQR. Alright, please again pause the video right now so that you could actually answer this question. The suggested time frame for you to draw the box plot is 5 minutes, which should only theoretically take you 2 minutes or so. So if you were to put this information and represent this as a box plot, this is the diagram that you should have. And please note that I've actually labeled my particular box plot. So I've given it a heading because there is a context, there's a scenario that kind of indicates what I need to include. Because this is talking about the amount of time robins, which is a type of bird, spends in the garden. So in this case, this will be about amount of times in garden, which is in minutes, which is the units in this case. Once you've done that, the question then asks you to compare the distribution of time spent in the garden by robins and sparrows. So over here was in part A. Now this over here is the graph that shows you the amount of time spent by sparrows. Now, if I was to compare this, remember, you need to compare it by the SOX, which is the shape, the outliers, if they have any. Then you talk about the center, followed by the spread. And generally, you do this in this particular order. So let's firstly talk about the shape. In this case over here, now remember there are different definitions of the shape, so it's up to your judgment to say what it is. But in this case over here, I would say that this one is going to be negatively. So the shape of the sparrows has a negative, so that's what I've said over here. In contrast, the shape of for the robins in this case has a slight positively skewed. Once I've done this, I then discuss what are the center values of each. So I said on average, both birds spend the same amount of time on Tom's garden. So as you can see over here, the median values are identical. However, there are differences in terms of the IQR as well as the range. And that's pretty much what I've discussed over here. So this is pretty much how you would formulate your response. Make sure your response is based around this, the shape, the outliers, center, and spread. Again, this is for question 3, so please give yourself about 5-10 minutes for you to answer this question over here. So the question wants you to construct a box plot for this set of data and compare the two box plots in terms of its shape, center, and spread. So if this particular data set over here is already ordered from smallest to largest, so if I was to find out the minimum maximum, this is therefore going to be 220 and 400. To find out the my median, I cross out the numbers from the end and work my way towards the middle. So if I do this, I should get a median value equal to 312. To find out Q1, that's the median of the lower half. So in this case over here, these are the data of my lower half. These are the data for my upper half. 252 is therefore going to be my lower quartile, and therefore 332 is going to be my upper quartile value. Now, once you've done that, it should be quite easy for you guys to actually draw the actual box plot. So since this is a parallel box plot, I'm going to draw it on top of the one that's already provided in the question. And then I'll just label it as so you can actually see which box plot corresponds to which particular age group. Now, once you've done that, then you can actually compare the actual box plots. So if you do this again, make sure you're comparing based on its shape, center, and spread, as well as outliers if it's present. If you did that, then your answer in this case should be something similar to my answer as shown below. So I said the distribution for the reaction time, notice again I'm including the context, for both the 20-year-old and 30-year-old were negatively skewed. The average reaction time for the 30-year-olds is slower. It's low because it where is it? Because it's got a higher value, so a higher yes, that's right. If your reaction time is higher in value, that means you're slower. I kind of just confused myself a bit just then. And I provided the values. Always provide numerical values when you're actually writing your response, just to support your answer. Then I said both distributions have no outliers. However, the reaction times are more varied with the group of 30 years old, as they have a greater range in IQR values. And to make this answer even more better, then you would include the values, but obviously I kind of didn't have space, so I didn't actually bother including it at all. We're now going to be actually looking at normal distributions, and since your cat since we no longer have access to the CAS calculators, you're going to be expecting a lot more questions on your exam as well as your assessments related to normal distributions, just to compensate for that. So it's very critical that we do revisit this so you have a good understanding. We say that a normal distribution is essentially a bell-shaped curve, and the mean, median, or mode, any one of these values can readily be found in the middle where it has the tallest peak, in this case over here. Most of the values are clustered around the center, and the area under the graph of a bell-shaped curve or under a normal distribution is equivalent to 100%. So as you can see, if you split the normal distribution in half, then obviously this is going to represent 50% of the data, this is going to represent the other 50% of the data set. These are the kind of things that I'm expecting you guys to do related to the normal distribution. So you should be able to identify the mean, median, mode, which everyone should be able to do. Comment on the shape, which is, we said it was a normal distribution. It is symmetrical in this case. Identify the standard deviation. Distinguish which data set has a smaller or greater standard deviation, and compare the mean and standard deviation between multiple normal distributions. So in the first example over here, what is the mean trunk diameter? So again, we said that it's where it has the tallest peak, so therefore it's going to be 150 centimeters. Make sure you're including units if applicable, and describe the shape of the distribution. In this case, that's just going to be symmetrical. Example number 2, which of the following has the smallest mean? So remember, your x values over here corresponds to like the size of the values. So something with the smallest mean is going to be more it's going to be found more on the left hand side. So therefore, this one over here will have the smallest mean in this case. Now, generally for a normal distribution, you could either find a normal distribution that looks something similar to this, or you could find a normal distribution as shown in the diagrams I have here, where they're actually divided into these little sections with the exact same width length. One of the great things about this is that when it's actually been divided already, the distance between this over here to the actual center tells you the size of the standard deviation. So we say that the standard deviation is size of the width. So this over here is the width when a normal distribution has been divided equally. So in this example over here, the difference between 85 and 100, that's going to be 15. And that's the same case for all of them if you keep increasing. So in this case, if we're trying to find out the standard deviations for both of this, the first one is going to be 2, and then the next one is going to be 30. So this is pretty straightforward right now. We then talked about a particular rule that's related to normal distributions. This is referred to as the 68%, 95%, and the 99.7%. The way that this rule works is we said that if we move one standard deviation to the left as well as to the right of the mean, this will encompass 78% of the data set. If we move 2 standard deviations from the mean, so moving left as well as right, this would encompass 95% of the data set. And if you move 3 units to the left and right, this will encompass 99.7%. This is a rule that you just have to memorize. And based upon this rule, we can then answer the following questions. So the first question reads, what percentage of women are between 62 and 67 inches tall? So 62 lies over here, 67 is over here, your mean is over here. We said that if we move 1 unit to the left and to the right, this is 68% of data. So therefore, in this case, 68% of women are between 62 and 67 inches tall. Question 2, what is the range of heights between which about 95% of the women fall? So that's going to be moving 2 standard deviations from the left and right from the mean. So in this case, the answer will be from 59.5 to 69.5. So that will be your answer for part 2. You should actually include inches as well. What is the range of heights between which nearly all over 99% of women fall? So that's pretty much 3 standard deviations, because that's 99.7%. So therefore, this answer is going to be 57 to 72 inches. Make sure you're including units in your answers. What percentage are taller than 67 inches? So this is now where it gets slightly more tricky. So it's asking, so above 67 inches, that's this area over here, which I'm about to shade. So all of the area that I'm shading in red right now is where women have a height greater than 67 inches. Now, we know previously that if you move 1 unit to the left and 1 unit to the right, this encompasses 68%. Okay, so we know that this is 68% over here. So I'm going to represent that by just kind of shading in this area over here. If this is 68% and we know that 100% of the data set is everything under the graph, we can find what this is by going 100 subtract 68. Okay, now if you do that, you're going to get an answer of 32%, and 32% represents this as well as this over here. But since we're only interested on this side over here only, it's pretty much going to be the half of 32. So therefore, it's going to be equal to 16% in this case. What percentage are shorter than 59.5? So it's asking for all of these ones over here. I know it's a bit messy right now, but please just endure it a bit. So you're trying to find out what this percentage is made up of. Now we know that if we move 2 standard deviations from the left and right, this includes 95% of the data set. So in order to find this, what I'll do is, since I know that from here to here is 95, I can find out the remaining leftovers, as this will give me these 2 shaded parts over here, which I'm shading over here. So this, and then I can half that to find out just this side over here. So in this case, the leftover from 100% is going to be equal to 5%. And then I divide that by 2, and that will give me an answer of 2.5%. Moving on to our next example over here, the question reads, the heights of 250 20-year-old women are normally distributed with a mean of 1.68 meters and a standard deviation of 0.06. So I've already wrote down where the mean lies, so that's where the peak of the normal distribution is going to be. And to find out the other values, which is generally not given to you, all you need to do is just add and subtract 0.06 from it to fill out the remaining numbers. Part B says, find the probability that a woman has a height between 1.56 meters and 1.74 meters. So it's essentially asking for this area over here. Now, to answer this particular question, I'm going to be relying on my knowledge of the 68% rule, the 95% rule, and the 99.7% rule. So we know that if you move from one standard deviation from the left and right, this is 68%. So therefore, since moving one unit to the left and one unit to the right is 68%, we know that this over here is equal to 34%. This is also equal to 34%. And I know that if I move 2 units to the left, this is therefore going to be 95. But also, what this essentially means is that from here to the midpoint, that's going to be half of 95. So the half of 95 is 47.5 in this case. And since I know that this is 47.5, and I know that from here to here is 34, all I simply do is add 47.5 with 34 to find out the answer for part B. If you do this, the probability is therefore going to be 81.5%. Alright class, what I'd like you to do now is I'd like you to please answer this question over here to test your understanding. You've got 10 minutes to complete this question, so please pause the video right now so you can actually work on it and then compare your answers once you finish the question or once 10 minutes is up. The first question wants you to sketch the distribution, so you need to extract the information from this scenario over here so that you can actually represent this on a normal distribution. It says that the mean is 22.8, so that's going to be over here where the highest peak represents. And it tells you that the standard deviation is 1.1. So what I'm going to do first is find what this value is. So to do that, I just go 22.8 plus 1.1, and I add 1.1 repetitively to find out the other values. To find out what this value over here is, I'm going to go 22.8 subtract 1.1 and continue repeating it. Repeat this subtraction to fill out the other values over here. And once I do this, I need to ensure that I'm labeling my normal distribution. And since we're talking about head circumferences in this example over here, my label is going to be head circumferences, and I'm including the unit in brackets, which is inches. Now I'm going to answer part B. Part B asks us, what percentage of soldiers have head circumferences greater than 23.9% or 23.9 inches? That's essentially represented by this blue shaded area over here, which I've done. So we need to find what this shaded area is as a percentage. Now, in order to do this, I'm going to rely on my knowledge of the 68% rule. I know that if I move one unit to the left and right, this is 68% over here. Now, to find out what this blue area over here is, what I can do is I can go 100 subtract by 68, because by doing so, this will give me these areas over here. So 68 is from here to here. If I go 100 subtract 68, it will give me the outer areas. Since I'm only interested in the area on the right hand side, because I want to find things that's greater than 23.9, I then divide that by 2 to find the answer. So first, 100 subtract 68 is 32%. And since I'm only interested on the right one, I go 32 divided by 2, which is therefore equal to 16%. Part C says, what percentage of soldiers have a head circumference between 21.7, so it's over here, and 23.9? Notice that both of these values lie one value away from the standard deviation, so therefore the answer is going to be 68%. So I made a typo over here. The answer should be 68%. And for part D, what percentage of soldiers have a head circumference that's less than 26.1? So you're pretty much trying to find all of this shaded area over here. That's what you want to find. And in order to answer that, we know that since 26.1 is 3 standard deviations away, I'm going to go 100 subtract 99.7%. If I do that, that gives me 0.3%, and that 0.3% that represents the unshaded areas on the sides of it, on each side of the normal distribution. Since I'm trying to find from here all the way to here, in this case over here, so I'm trying to find out all of this, and I know that in this case over here, each of these represents 0.15. I can go 99.7% plus by 0.15, and that will give me an answer of, oh, sorry, there's a typo, 98.85% as an answer. Again, please pause the video right now so you can answer this question. Again, if you're trying to answer this question, this is what you should have as your graph. And if you're trying to find out the percentage of the scores that lie between 210 and 690, this is represented over here. The answer should be 95%. This is 34%. This is 47.5%. This is going to be 81.5%. Question 3, again, please pause the video right now so you can answer it. And after you do that, these are the answers that you should arrive to. Alright, now once you've actually finished answering those questions, we could then move on to what bivariate data is. So bivariate data is looking at data sets that contain two variables. And the purpose of this is so we can actually analyze, compare, and explain the correlations for how are these two variables are related to one another. We said that bivariate data includes two variables, and one of the variables generally has an impact over the other. We refer to these variables as the independent variable as well as the dependent variable. So the independent variable is the one that's influencing or has an impact on the other variable, and the dependent variable is what you're actually measuring. And I've got those definitions over here. One way to remember where the IV and dV goes when you're actually graphing this is that the dV is always on the x, because you can kind of write the letter D with the y-axis. So dV goes over here, and if you flip or rotate your head around, this over here is essentially an I, and you can write V here. So the independent variable is always plotted along the x-axis. The dependent variable is always plotted along the y-axis. So we need to be able to identify what is the independent variable and dependent variable from a particular problem. So in this case over here, temperature and ice cream sales, what is the IV? Well, in this case over here, the temperature will influence how many ice cream sales that you will generate. So therefore, temperature is going to be the IV. What we kind of covered in the last week of the term was that we said that another way of referring to the independent variable is the explanatory variable, and that's probably more commonly used than the independent variable in the mathematical context. So again, explanatory variable is a thing that's impacting. Another way of representing or referring to the dependent variable is the response variable over here. I've got some questions over here that I'd like you to do, so please try to answer these questions within the next 5 minutes. So please copy down the questions inside your exercise book and complete them for me, please. So for the first question, in questions that involve weight and height, which one of the is height more likely to be a response variable or an explanatory variable? Well, as you're probably already aware, the taller that someone is, generally the more heavy there is. So in this case, height is going to be the independent, because that's the one that has the impact in this case of it. It will influence the other variable. Part 2, a nutritionist wants to determine if the amount of water consumed each day by persons of the same weight and on the same diet can be used to predict individual weight loss. So these are essentially two variables over here, the amount of water consumed and weight loss. In this case over here, your explanatory variable is the amount of water, because this will explain why you've lost weight. Part 3, an insurance company hires somebody to determine whether the number of hours of safety driving classes will have an impact pretty much on the number of driving accidents. So therefore, this over here would explain why you'd have a different number of driving accidents. So explanatory variable would be number of hours of safety driving, and this is the response variable, and this is the answers for the last question over here. Hopefully you guys got this correct. Okay, now we're going to be looking at the final part of today's lesson, where we're going to be looking over scatter plots. So scatter plots are used to illustrate the correlation, so meaning the relationship between these two variables or not. A line of best fit is typically drawn on these scatter plots, which is essentially a straight line that best represents all the data on a scatter plot. By drawing this line of best fit, we can see whether the relationship is going to be a linear one or whether it's going to be a non-linear one. Now, when you're drawing this line of best fit, which we're going to talk about a bit later on, this line of best fit may pass through some of the points, it may pass through none of the points, or through all the points. It will vary depending on where the actual dots are placed. And as I said before, it's used to show how these two sets of data are related to one another. Now, when we're talking about the correlation between these two data sets over here, we said that the correlation describes the strength, the direction, as well as the form of the relationship. So now I'm going to be unpacking what I mean by strength, direction, and form. So in terms of direction means, is it moving in the positive direction? Is it moving in the negative direction? Or is there no correlation at all? So you already know what a positive one looks like. So positive is when one variable increases, the other increases. Negative correlation is when one variable increases, the other variable actually decreases, which is why it's actually going down in this case over here. When we're talking about a strength correlation, we're talking about is it classified as weak, is it classified as moderate, or is it classified as strong? And there are two subjective ways that you'd actually determine the strength of correlation. One of them is by looking at the density of all the individual points, and those points that are more closer to the line of best fit are classified to be a strong. So whereas any points that are kind of further away or further away from the line of best fit are considered to be weak. Another way that you can kind of determine the strength of the line of best fit or the correlation is by looking at the gradient of the line of best fit. Generally, a steeper gradient implies a stronger relationship, whereas a smaller steep indicates a weak correlation. But the way that we actually accurately determine the strength of correlation is by determining something referred to as Pearson's correlation coefficient. So we've kind of done this previously last term, and we required the CAS calculator for us to do that. Since we don't have the CAS calculator anymore, you're going to have to eyeball it and just see whether it's strong or not based on how clustered the individual dot points are going to be. So again, as I said, strong. As you can see over here, all the dot points are close to the line, and the more weaker it goes, the more scattered and further away these points are from the line of best fit. So we're now going to be looking at the form of the correlation. So when we're talking about the form, we're kind of asking, is the correlation linear or non-linear? So the first one over here, this is linear because if I draw a straight line, this kind of goes in that direction over here. Now notice in the second example, this is non-linear because it goes linear initially, but then it kind of spikes up. So this is therefore not following a typical straight line. So therefore this is non-linear, and the other one is also obviously non-linear as well. Now, when you, most of the questions actually ask you to comment on the correlation between two sets of variables or two sets of data. So I provided a template for you already, and you need to use this template in order to comment on the strength, direction, as well as the form. So we're going to be looking at examples over here of where you could actually apply this particular template. So using this example over here, the temperature versus the number of ice cream sales. So in this case over here, because most of the data points are kind of found along the line of best fit, I'm going to say this is relatively strong. Because both of them are increasing, this is therefore a positive relationship. And also, this also follows a straight line, the trend of a straight line, so therefore it's going to be classified as linear. You also need to state what the variables are, so that's what these two spaces are, so therefore it would be temperature and sales. What we're going to be looking at next is the line of best fit, because it's very important that you know how to draw a line of best fit and what are the guidelines in order to draw a line of best fit. We kind of said before that it's used to show how two sets of data are related, and it's very useful to make estimations of a particular variable from the equation, and we're going to be looking at this in future lessons. So this is talking about interpolation and extrapolation. So as I said earlier on, drawing the line of best fit is subjective. So what that means is if I was to draw a line of best fit for one set of data and you were doing the exact same thing, our lines of best fit will be different, and we're going to have different equations therefore for our line of best fit. So this means that each person will have a different gradient. The number of points found above and below the line will be different as well, and the number of points the outlines of best fit will go through will also differ as well. So these are the three guidelines over here. The key word in this case is the word roughly. You want to roughly have the same number of data points found below and above the line. So in this case over here, you've got 1, 2, 3 that's found above the line. You've got 1, 2, 3 that's found below the line. So that's, again, the keyword is roughly. You might have, for instance, if you have a different example, you might have 5 above, you might have 6 below. That's okay as long as it's kind of symmetrical in this case over here. Second part, dot point says you should try to minimize the distance of data points away from the line of best fit on each side, so from the above and below. So what I mean by that is these distance over here are relatively the same, so you're trying to make things even in this case over here. And lastly, my last dot point is choosing appropriate scales and intervals. Now that's not related to drawing the line of best fit itself, that's more drawing the actual scales for your scatter plots. So for instance, in this case of here, this is inconsistent class intervals because usually if you have the same width size, they should increase by the same amount. This goes up by 2, but then this goes up by 1 for the exact same width. So therefore this is considered to be inconsistent class intervals. It should be something like this over here, and you should include these zigzags if you're skipping values. So now they go up by the same amount, which is going up by 2.5s. These over here are examples that I've drawn the line of best fit to. So notice that over here, they kind of have roughly the same number of dot points found below and above. Now, when you have an outlier over here, I don't need to cater my line of best fit to the outlier at all, because remember, outliers generally are not supposed to be part of our data set at all. Doing another example of where to draw the line of best fit. If I also draw a line of best fit, this is what it would look like. And for this example over here, doesn't even look like any correlation at all, so you cannot draw a line of best fit. So again, I do want to emphasize, you cannot draw a line of best fit for any scatter plots that appear to have no correlation at all. Now, these are some of the questions that I kind of asked you guys to complete over the holidays, I believe. So if you haven't done that, please make sure you complete that off. For part A, what you need to do is you need to describe the type of correlation. So what that means is use the template over here to answer part A. Part B says, what is the practical interpretation? So using the context, explain what does it mean based on the graph shown. And part C, you need to practice drawing a line of best fit. So what I recommend you do is either print out these worksheet questions over here so you can actually answer it, and then please email it to me so I can see how well you actually did. So there's this question of it, this worksheet, as well as this, and I think there's about one more, so there's 4 questions in total. This is the end of the video. Thank you for watching, guys. If this video was helpful, please leave a thumbs up. See you in the next video.